Okay, let's dive into this. Multi-threaded programming. Just hearing that, especially with thread safety thrown in, it kind of makes your head spin, doesn't it?
Oh yeah, it feels like one of those super complex, maybe even scary computer science topics.
Right, like trying to juggle chainsaws. But the thing is, almost everything now has multiple CPU cores. Your phone, your laptop, servers.
Exactly. And if your code can only do one thing at a time, well, you're just not using the hardware efficiently.
Yeah.
You're leaving performance just sitting there.
Which used to mean, in Ruby anyway, maybe using multiple processes, forking.
Yeah, forking works.
Hmm.
It was the standard way for a long time. But it's heavier. Processes have their own memory. Starting them takes more effort.
So threads are supposed to be cheaper, lighter.
That's the promise. Lower overhead, and crucially, they share memory, which is powerful.
And also where all the trouble starts.
Pretty much. Yeah, shared memory is the heart of the complexity.
So we've been digging into some material on Ruby threads, really trying to get under the hood, understand what's going on, why it's tricky, and, what tools Ruby actually gives us to handle it.
Yeah, the goal here is to cut through that feeling of complexity, pull out the key ideas, maybe dispel some myths, and give you a better handle on concurrent code.
And the first surprise, maybe, is how fundamental threads are. Like, you're always in one.
Always. Even in the simplest script, that first thread, the one that starts everything, is the main thread.
You can actually see it, right? Like an herb thread.main.
Yep, thread.main gives you that object. And thread.current, well, that tells you which thread you're executing in right now.
So at the start, thread.current is the same as thread.main.
Initially, yeah, but thread.current changes. If you launch a new thread with thread.new and call thread.current inside that thread's block, you get a different thread object. It represents that new execution path.
Okay. And that main thread, it's special, like if it stops.
The whole show stops. If the main thread finishes, the whole Ruby process exits, taking all other threads with it. Boom, gone.
But other threads can finish on their own without killing everything.
Right, they just complete their work and disappear. The main thread's the anchor.
So we have these multiple threads of execution, paths through the code, all sharing memory.
Lightweight because of that shared memory, yeah. But again, sharing is caring and also dangerous.
And these aren't just some Ruby abstraction, are they? Like MRI, JRuby. They use real OS threads.
They do. When you do thread.new, the underlying Ruby implementation, at least the common ones, asks the operating system to create and manage a native thread.
So you could actually see them in top or activity monitor or whatever.
Yep. The OS is scheduling them, running them on your CPU cores.
Which brings us, I think, to the really mind-bending part.
The context switching. Non-deterministic context switching.
Okay, yeah. Break that down. Non-deterministic context switching sounds complicated.
It's the OS thread scheduler. It's deciding constantly which thread gets to run on a CPU core now. It runs thread A for a tiny slice of time, pauses it, saves its state.
And swaps in thread B. That's the context switch.
Exactly. And non-deterministic just means, well, you can't predict when it's going to happen.
At all. It could happen mid-calculation, mid-sentence.
Pretty much. It can happen between any two machine instructions. And that's the core difficulty. You can't just read your code line by line and know the exact order things will happen across threads.
It's like the rules of physics suddenly get weird. You're running along and suddenly, zap, you're paused and someone else is running.
Precisely. The material had this great simple file uploader example with a line like at results, q.new.
Oh yeah, seems so simple. Or equals, set it if it's nil.
Looks simple, but under the hood it's really 3 steps. 1, check if at results is nil. 2, if it is, create a new q object. 3, assign that new object to at results.
Okay, so walk me through the disaster scenario. Thread A comes along.
Thread A hits the line. Step 1, is at results nil? Let's say yes, it is nil. Step 2, okay, create a new queue. Done. Now before step 3, the assignment. Bam. Context switch. Thread A gets paused.
Holding its shiny new queue, ready to assign it, but pause.
Right. Now thread B gets its turn. It hits the same line. Step 1, is it results nil?
Well, thread A never assigned anything, so yes, it's still nil for thread B too.
Exactly. So thread B also does step 2. Creates its own new queue object. And let's say thread B gets lucky, it completes step 3. It assigns its queue to at results.
Okay, so at results now points to thread B's queue.
Now thread A wakes up. It was paused after creating its queue just before assignment, so it just continues.
And does its assignment step. Step 3, assigning its queue.
Right over the top of thread B's queue. Whatever thread B put in its queue, maybe some results, is potentially lost.
Yeah.
Our results now points to thread A's probably empty queue.
Wow, okay. That's a race condition
Yeah.
caused by that unpredictable interruption right in the middle of what looked like one operation.
Yep. And it highlights the fundamental issue. Problems happen when multiple threads try to change the same thing concurrently, and the OS can interrupt them at basically any point.
So it's not that equals is inherently evil, it's just risky when used on shared stuff that multiple threads might hit at the same time.
Exactly. The solution is either don't let them modify the same thing concurrently, or
Protect it somehow when they do.
bingo. Which leads us to the tools Ruby gives you.
Right, the thread API. You might require thread for some helpers like queue, but thread itself is built in.
And you start threads with thread.new, or thread.start, thread.fork. They're aliases mostly.
What are the main ways we interact with them once they're running?
Join is probably the big one. Some thread.join.
And that just means wait.
Yeah, the current thread stops and waits until some thread finishes its work.
So if my main thread kicks off a bunch of worker threads, I can join them all at the end to make sure everything's done before the program exits.
Exactly. It's essential for coordinating work. And join has another really important job. Exceptions. If the thread you're joining died because of an unhandled exception, join will re-raise that same exception in the thread they called join.
Whoa. So the error propagates back.
Yep. We saw that example where a thread just did raise hell. The main thread called join, and boom, the main thread crashed with that hell exception. The backtrace even points to the original raise in the other thread.
That's actually super useful for tracking down problems. What about for tag value?
Similar to join. It waits for the thread to finish, and it returns the result of the thread's block, whatever the last expression evaluated to.
Does it also re-raise exceptions?
It does. It calls join internally, so you get the waiting and the exception propagation and the return value.
And thread tag status just tells you if it's running, sleeping, dead, whatever.
Yep, just a status check. The material also warned against using thread hag raise or thread hag kill.
Right. Seems like pulling the plug forcefully. Probably bad for cleanup.
Generally asking for trouble, yeah. Stick to join and value for managing threads you start.
And it's good that this basic API works across MRI, JRuby, Rubinius, even if they handle things differently inside.
That internal difference is key, though.
Yeah.
It leads to this super important point. Concurrent is not the same as parallel.
Okay, I hear this a lot. Explain it. We have multiple threads. Isn't that parallel?
Not necessarily. Think about it like tasks and workers. Serial is one worker doing task A, then task B. Simple.
One after the other. Got it.
Concurrent is one worker juggling task A and task B. Maybe they work on A for an hour, then switch to B for an hour, back and forth. Both tasks make progress over the day, but the worker is only ever doing one thing at any given instant. That's concurrency, managing multiple tasks over time with shared resources.
Okay, so multi-threading makes my code concurrent. It's structured to handle multiple things.
Exactly. Parallel is when you hire a second worker. Worker 1 does task A, worker 2 does task B at the same time on separate desks, maybe. They run simultaneously. That requires more resources, 2 workers, but finishes faster.
So writing thread.new makes my code concurrent. But whether those threads run in parallel depends on the Ruby interpreter and the OS.
Precisely. You enable parallelism by writing concurrent code, but you don't force it. The runtime environment decides if it can and will run them simultaneously on different cores.
Which brings us to the GIL, the Global Interpreter Lock in MRI.
Ah, yes. The infamous GIL.
What is it actually doing?
In MRI, the standard Ruby, it's basically a giant lock around the Ruby interpreter itself. Only one thread can hold the GIL and execute Ruby code at any given moment.
Even if I have 8 cores and 8 threads ready to go?
Even then, only one thread gets to run Ruby instructions at a time. The others have to wait for the GIL to be released.
So in our worker analogy, it's like there's only one keyboard and only one worker can be typing code at once.
That's a decent way to think about it.
Yep.
And you see the effect clearly in benchmarks,
Yeah.
CPU-bound stuff, like pure math calculations.
Like calculating prime numbers in the examples.
Right. Adding more threads in MRI gives you almost no speed up, because they all get stuck waiting for the GIL.
Yeah.
The computation itself is serialized.
The graphs also showed that for IO-bound things, like fetching web pages.
Ah, yes, IO-bound tasks. Things where the thread spends most of its time waiting for something external, like the network or the disk.
Adding more threads did help there in MRI. Performance got better. Why?
Because when an MRI thread is blocked on IO waiting for that network response, say it releases the GIL.
Ooh, okay, so while thread A is waiting for Google to respond, it drops the GIL.
And thread B can grab the GIL and run its Ruby code, maybe make its own network request or process some data.
So you get concurrency, making progress on multiple waiting tasks. Even if you don't get parallel Ruby execution, it keeps the CPU busy doing something useful instead of just waiting.
Exactly. That's where threads still provide a big benefit in MRI for I/O-heavy workloads.
So why have the GIL at all then, if it prevents parallelism?
History and simplicity, mostly. It protects MRI's internal C code from race conditions without needing lots of complex, fine-grained locks everywhere inside the interpreter.
Easier to manage one big lock.
Yeah. And also made writing C extensions simpler because extension authors generally didn't have to worry about their code being called by multiple threads simultaneously unless they explicitly released the GIL themselves.
Okay, crucial clarification time. Does the GIL make my Ruby code thread safe?
No, absolutely not. That's maybe the biggest misconception out there.
Okay, say it again for the people in the back.
The GIL does not make your Ruby code thread safe. It just makes race conditions less likely to occur or harder to reproduce in MRI because it prevents simultaneous execution of Ruby code.
But the underlying problem in your code, like that at results equals the q.new issue, is still there.
Still there. The GIL might just, reduce the odds of the context switch happening at the exact wrong microsecond. But it can still happen.
And what about JRuby and Rubinius? They don't have a GIL, right?
Correct. They achieve true parallelism for Ruby code execution by using different strategies, like more fine-grained locking internally or relying on the JVMs, in JRuby's case, thread safety mechanisms.
So CPU-bound code does speed up with more threads on JRuby Rubinius.
Yes. But the flip side is any race conditions in your Ruby code are much more likely to surface because threads really are running in parallel and hitting shared data simultaneously.
So they kind of force you to write properly thread-safe code if you want to use threads effectively.
You could say that. They don't hide the problems the way the GIL sometimes can.
Okay, this leads to a very practical question. How many threads should I actually use?
'Cause it's
5, good. 50, 500.
the million-dollar question. And the answer, annoyingly, is it depends.
Of course it does.
You have to measure. Creating threads is pretty cheap these days. You can often have thousands running. But managing them, the context switching, that has overhead.
And it depends heavily on I/O-bound versus CPU-bound work and the GIL.
Massively. For I/O-bound work, where threads spend time waiting, you often need more threads than CPU cores. Remember the NY times fetch example. Performance improved up to maybe 10 threads on a 4-core machine before the context switching overhead started to hurt. If your I/O is really slow, you might need even more threads just sitting there waiting.
Okay, so for I/O, maybe significantly more threads than cores. What about CPU-bound?
For CPU-bound work, you generally want a number of threads close to the number of CPU cores if you don't have a GIL. Like on JRuby or Rubinius, the pi calculation graph peaked around 4 threads on 4 cores. More threads just caused more context switching thrash for no gain.
And on MRI for CPU-bound.
Because of the GIL, more than 1 or maybe 2 threads doing heavy CPU work gives basically zero benefit. They just fight over the lock.
So real apps are usually a mix.
So you benchmark, test your actual workload on your target platform and hardware, find the sweet spot.
Let's nail down thread safety again. You said it's not about crashes per se.
Right. It's about protecting the integrity of your data in memory, preventing it from becoming inconsistent, corrupted, or just plain wrong because multiple threads messed with it concurrently.
These bugs are sneaky, right? Hard to reproduce.
The worst, Heisenbugs. They appear under load, then vanish when you try to debug them because debugging changes the timing.
We had the example. What was the other one? The order payment.
Yeah, the order hashtag collect payment method. The idea was you only want to charge the customer once. So the code checks if order.pending before processing the payment.
Seems reasonable.
But imagine 2 requests, 2 threads for the same order hit that concurrently. Thread A checks order got pending. Yes, it is. Before it can update the status. Context switch.
Oh boy, here we go again.
Thread B runs. It checks order.pending. For thread B, it still is pending because thread A didn't update it yet. So thread B also proceeds into the payment logic.
Result, double charge.
Potentially, yes. Even if the actual payment processing inside the method was somehow protected, the decision to proceed was made by both threads based on stale information. The check and the state change weren't atomic together.
Okay, so is anything in Ruby standard library thread safe for modification by default? Like, can I safely push to the same array from multiple threads?
Nope. Array hashtag push is not thread safe for concurrent modification. Neither is modifying a hash. We saw that example. Multiple threads doing shared array nil. On MRI, because of the GIL, you might get lucky and see the correct final size often. But on JRuby and Rubinius, with true parallelism, you almost certainly see fewer elements than expected because updates get lost.
Even basic stuff like counter plus one.
Not atomic. That's a read, an add, and a write. Can be interrupted.
So the rule really is, assume shared mutable state is not safe for concurrent writes unless you know otherwise or you protect it.
That's the safest assumption, yeah. These operations are perfectly fine if only one thread is doing them, or if threads are modifying different objects. Yeah. It's the same object, multiple threads modifying combo that's dangerous.
Right. So how do we protect it? What's the main tool?
The mutex, mutual exclusion. It's basically a lock.
Like a bathroom key, only one person in at a time.
Exactly like that. You create a mutex object, and then you wrap the code that needs exclusive access, the critical section, inside mutex.synchronize.
And how does that work?
When a thread hits synchronize, it tries to acquire the mutex's lock. If it's free, the thread grabs it, goes into the block, does its work.
What if another thread already has the lock?
Then the second thread waits. It blocks. It just sits there until the first thread finishes the block and automatically releases the lock.
Synchronize handles the release automatically, even if there's an error.
Yep. It ensures the lock gets released. That's crucial. And we saw it fix the shared array nil problem. With the mutex.synchronize around the push, every thread got its turn, and the final count was correct on all platforms.
So for the order hashtag collect payment bug, we need to wrap the whole thing, the check and the payment part.
Yes. The critical section is the entire sequence. Check if pending, if yes, process payment and update status. That whole chunk needs to be inside the mutex.synchronize.
If you only put the mutex inside the payment part after the if check,
you wouldn't fix the root problem. Multiple threads could still pass the if check concurrently before any of them acquire the lock. They'd still all try to pay, just one at a time inside the lock. You have to lock around the decision and the action.
Makes sense. What's the catch with mutexes? Performance?
Performance, yeah. They serialize execution. If code inside a mutex is contended, lots of threads want it, it becomes a bottleneck. So you want your critical sections to be as small and fast as possible while still being correct.
And they can cause deadlocks.
Ugh, yes. The dreaded deadlock. Thread A has lock 1, wants lock 2. Thread B has lock 2, wants lock 1. Neither can proceed. Stuck forever. It's a classic trap when using multiple mutexes.
Okay, so mutexes control access. What if one thread needs to wait for another thread to make some condition true, like wait until there's data in a queue?
Ah, good question. That's where condition variables come in. They work together with a mutex.
How so?
Think producer-consumer. A producer thread adds items to a queue, a consumer takes them out. The consumer needs to wait if the queue is empty.
Instead of spinning in a loop checking queue.empty.
Exactly. Busy waiting is bad. Instead, the consumer acquires the mutex guarding the queue. It checks if the queue is empty. If it is, it calls convar.wait mutex.
Okay, convar.wait. What does that do?
Two crucial things. It puts the consumer thread to sleep, and it atomically releases the mutex.
Releases the mutex. Why?
So the producer thread can acquire the mutex, add an item to the queue, and then signal the condition variable.
How does it signal?
It calls convar.signal, wake up one waiting thread, or convar.broadcast, wake up all waiting threads.
And when the consumer wakes up from wait?
It atomically reacquires the mutex before continuing. So it can safely check the queue again, or take the item. It avoids busy waiting and ensures safe access.
Okay, that's clever. Mutex for access, condition variable for signaling changes while holding the mutex, mostly.
It's a fundamental pattern for coordinating threads based on state changes.
All right, so we have threads, race conditions, mutexes, condition variables. How do we actually write code that uses this stuff safely without going crazy?
Well, one interesting point from the material was that often just writing good, clean, idiomatic Ruby can get you part of the way there. But you need that awareness layer.
What are some practical rules or things to look out for?
Big one. Avoid mutating global state if you can possibly help it. Globals, constants you modify, class variables used for shared runtime state. These are danger zones. If you must have shared global things, make sure they are inherently thread safe or protected by a mutex.
Okay, minimize shared mutable stuff. What else?
Prefer creating new objects instead of modifying existing ones in place, especially if they might be shared. Functional style helps here.
And for resources like database connections, create one per thread.
Using thread locals, thread.current.db is one way. Each thread gets its own instance. Or, even better,
use a connection pool.
Exactly. Use a library like connection pool. It manages a pool of connections safely using mutexes and condition variables internally, so you don't have to worry about the low-level locking yourself.
What about autoload for loading code?
Avoid it at runtime in threaded MRI environments. It's not thread safe. Eager load your code up front, which is the default in modern Rails anyway.
And lean on thread-safe data structures when available, like Q.
Definitely. If Ruby gives you a thread-safe version of something, like Q, size Q, use it instead of rolling your own mutex around a regular array or hash if you can.
Finding these bugs still sounds really hard. Any silver bullets?
Sadly, no. It often comes down to careful code review, thinking explicitly about concurrency. What happens if two threads hit this code? And understanding where the risks are typically around shared immutable state. Load testing can help reveal issues, but it's not guaranteed.
How does this play out in the real world, like in a Rails app or Sidekick for background jobs?
The key concept there is the boundary. In web servers like Puma, each request usually runs in its own thread. The request is the boundary. In Sidekick, each background job runs in its own thread. The job is the boundary.
Meaning?
State that's local to that boundary is generally fine. Instance variables in your controller action. Safe, because that controller instance is only used by that one request thread. Instance variables in your Sidekick worker. Safe, used only by that job thread.
But don't share state between requests or jobs using globals or class variables.
Exactly. That's where you get into trouble. Don't use a class variable for current user or something like that. That state would be shared and overwritten by concurrent requests or jobs. Keep state confined to the request job boundary.
It feels like mutexes and condition variables are powerful, but also kind of primitive, like assembly language for concurrency.
They are the building blocks.
Uh-huh.
And the advice is definitely to wrap them up, hide them inside higher level abstractions. Your core application logic shouldn't be full of mutex.synchronize.
So create helper classes or methods.
That's one level. Like the file uploader could be refactored to use a helper method concurrent teach that handles the thread pool and synchronization internally, or you can go for even higher level models, like the actor model.
Actors. Tell me more. Sounds fancy.
It's a different way to think about concurrency. An actor is like an object with its own private state and its own thread, or managed thread. It only communicates with other actors by sending and receiving messages asynchronously through a mailbox.
So no direct method calls on shared objects, no shared memory issues.
Largely, yes. The actor processes messages from its mailbox, one at a time. Its internal state, instance variables, is only ever touched by its own thread, so you don't need mutexes inside the actor to protect that state.
That sounds much simpler, potentially.
It can be. Sidekick uses Celluloid, which is an actor framework. The Sidekick manager actor might have internal arrays like @ready or @busy, but those are safe without locks because only the manager's thread accesses them. Communication happens via messages in queue this job, job finished, etc.
So it replaces direct calls and shared state with message passing.
That's the core idea. It shifts the complexity. Of course, the actor framework itself, like Celluloid or Akai in the Java world, uses the low-level primitives internally to manage the actors and mailboxes. And things like Puma's thread pool are implemented directly using mutexes and condition variables because that's infrastructure code.
Were there any other approaches mentioned? Atomic operations?
Yeah, brief mention of compare and swap, CAS, using the atomic gem. It's a hardware-level instruction for doing very simple updates, like incrementing a counter without a full lock. Can be faster, but only works for specific scenarios and needs careful handling.
And immutability, making data unchangeable.
Right. If data structures are immutable, can't be changed after creation, like those in the hamster gem, then sharing them between threads is inherently safe for reading.
But what if you need to update the state?
Then you typically create a new immutable structure based on the old one. The challenge then becomes safely updating the reference that points to the current immutable object. And for that, you might still need synchronization, often using CAS again, like the atomic.update example showed.
Wow. Okay. That was a lot. From basic threads to race conditions, the GIL, mutexes, actors, immutability.
It's definitely a deep topic. Concurrency is fundamentally about orchestrating work efficiently on modern hardware while keeping your data safe and correct.
It's a trade-off, isn't it? You don't need threads everywhere.
Absolutely not. Knowing where concurrency helps and where it just adds complexity is crucial. Sometimes the best concurrent code is single-threaded code.
But if you do need it, those rules seem key. Try not to share. If you share, share immutable. If you share immutable, you must synchronize.
That's a great summary of the defensive strategy.
I guess the final thought, looking at all this, Ruby's concurrency tools might have a reputation for being tricky, especially with the GIL history.
But the situation now, with native threads being the norm and solid libraries available, is actually pretty strong. You can build complex concurrent safe systems in Ruby.
So maybe the biggest hurdle isn't the language itself anymore. Maybe it's just us needing to really wrap our heads around how to think concurrently and manage state carefully.
That feels right. The tools are there, mastering the concepts and the discipline. That's the ongoing challenge for all of us.